So hello to everyone who's watching on YouTube. Since no one has joined the session in person yet, maybe we'll wait for 10 minutes before starting the session so that a few people can join the session in person. If no one joins, then we'll just get started anyways. Uh, hey RK Goyal. Uh, we are just waiting for a few more people to join the session in person. So we'll get started in let's say 10 minutes. Till then, I'll just mute myself. So today we'll be discussing the topics covered in this week, which was essentially some further reductions related to NP hardness, the reduction of NP hardness of 3-SAT and yeah, other stuff, along with basic introduction of randomized algorithms or something uh, approximation algorithms. Do you want some other thing to be discussed today? Do you have some specific doubts in some other topics? I can try to address them also. So what do you mean by complexity class of other types of problems? Oh, okay. So yes, talking about optimization or search variant. So usually, I think this was discussed in the lectures as well, or maybe we can discuss it today also. Uh, usually optimization, if you can solve decision problems, then you can also solve optimization problems because you can put do a binary search on the optimal value and solve decision problem in each iteration of the binary search if it makes sense. Or we can discuss it uh, as the session progresses. Oh, okay. So optimization variant seems harder than the decision variant. So like I said, actually it's not the case. Usually, like if we consider hardness in terms of let's say like polynomial time or non-polynomial time, then actually usually optimization variance, if the decision variant is like in the class P, then optimization variant is also in the class P. So maybe when we start discussing, I'll try to explain this also. Like we'll try to first explain this when we start the discussion. Like let's just wait for maybe 5 more minutes. So hi Mridula, we're just waiting for maybe like a couple of more people if anyone is else joining to join the session. Uh, so like we will get started in like 3 4 minutes. Till then, I'll just mute myself. Okay, so I guess no one else is joining the session, so maybe we can get started nonetheless. So, hi Arke and hello to everyone who's watching on YouTube. So, just to reintroduce myself, I'm Lakshya Saggi, the problem solving TA for the NPTEL Selected Topics in Algorithms course for the Tuesday 6 to 8 p.m. sessions. And this is going to be our this is going to be the session for the week 8. And in this session, we are going to talk about we are going to continue like talking about problems in and problems which are NP complete and uh, yeah, the topics which are covered in this week's lecture and some things related to approximation algorithms and stuff. So yeah, uh, so I guess we can get started. So I'll maybe just share my screen then. So let's just share my screen. So once again, like in the previous session, in previous week session also there was a lot of theory involved and not a lot of questions. So this week also, I guess, since these topics are highly theoretical, we'll be discussing more of theory or like summary of whatever was covered in this week's lectures rather than doing questions. Maybe we'll discuss a couple of questions, but yeah, not much more than that. So, Akil, I hope my screen is visible. Can you just point out if it is visible in the chat? Uh, oh, it's visible. Thanks. So before starting, maybe we can. So you had a doubt uh, between the decision variance and optimization variance, right? Okay, go ahead. So maybe we can discuss that first before moving on to like covering the summary for this week's session. So So essentially, what RK Goel has just said is what RK Goel told is yeah. So so what we have been discussing in the previous week and this week we have been discussing uh, the complexity classes for the decision uh, for decision problems. So we have been discussing just complexity classes for decision problems, and now but what about other problems? For example, optimization slash search problem. I believe this was your doubt, right? RK? Yeah. So essentially, okay. So maybe we can take an example, or maybe uh, uh, usually, or usually, or like most of the time, like I don't want to say always because I'm not sure if this thing is always true, but it is most of the time true. And that's why we cover only decision problems and not like optimization or search problems. If a problem, if a decision problem can be solved in polynomial time, then the corresponding optimization problem can also be solved in polynomial time. And the the and similarly for the search problem also. Similarly for the corresponding search problem. So maybe let's just take an example like uh, So maybe let's just take an example. So for example, maybe consider the vertex cover problem. So what's the decision variant of the vertex cover problem? This we discussed last week also. So essentially, suppose given a graph G uh, equal to V comma E, uh, does there exist a vertex cover of G with at most k vertices? So this is the decision version, right? Yeah. And so maybe let me just list out all of the variants. Like suppose I'm interested in solving decision version. Suppose I'm also interested in solving optimization version, and I'm going to show like let's just explicitly put out like what do we mean by optimization version, what do we mean by decision version. So yeah, so optimization version will say given a graph G equal to B comma A, does there exist or maybe uh, find the size of the vertex cover with minimum number of vertices. So suppose this is, let's say, the optimization version, and yeah. And then what will be the search version? So in the optimization version, we are just finding out the size. But let's say someone asks us to report the vertex cover as well. So yeah, so report the vertices of the vertex cover as well. So here it won't be find the size, but find the vertex cover with minimum number of vertices. So, first of all, like, are the like, why is it a decision variant? Because its answer is yes or no, and why is it an optimization variant? Because we are trying to minimize, like, we are trying to minimize or maximize, like, optimize the objective, which is size of the vertex cover. And why is this search version? Because we are actually trying to find the solution at which this optimum is achieved. So, are these uh, like, are the problems clear? Uh, RK Goel? Uh, RK, are the problems clear? Like, why are we defining these are some decision problems? Why are we calling one problem as the decision version? Why are we calling one as optimization, one as search? If there are some doubts, please let me know in chat. Oh, it's clear. That's nice. Okay. So now, suppose I have an algorithm A. So what I'm going to say is, suppose I have an algorithm. Suppose. So now what I'm going to say is if decision version can be solved in polytime, then optimization version can also be solved in polynomial time. So suppose we have an algorithm, or maybe I will list out this decision version, I'll call it as D, optimization version as O, and search version as S, right? Then suppose we have an algorithm uh, for D, uh, which runs in polynomial time. Then actually, or maybe like, yeah, or maybe we can just say which runs in time, uh, T of T. Uh, then, like, what is my claim? Then there also exists an algorithm for uh, O, which runs in time uh, T of T log n. like T of D multiplied by log of n, where n is like the total number of vertices in the graph. And uh, this is my claim. And why is this claim true? So like if this also suppose like first of all, why are we studying this claim? Like why am I even talking about this claim? So this claim is important because like you said, like why are we only studying the decision version of the problem? Why are we not studying optimization version or search version? And my goal is to say that okay, like because even if we classify the complexity of decision versions, like whether like it's in P or NP, then I also know whether it is easy or hard to solve the optimization version. So that's my claim. Uh, and to show this formally, like so formally, what this means is that if you have an algorithm for the decision version running in some time, uh, yeah, exactly. Yeah, so exactly like what you're saying, Archie, exactly. So you can call this decision variant log n times using a binary search like method to solve the optimization variant also. And that's why, so yeah. Oh, and you're saying that what if D is in NP? So actually, it can go the other way around also. So so this is maybe let's say claim one, uh, and then you can also have a claim two, and the claim two will be uh, suppose we have an algorithm for O, let's say for the optimization variant which runs in time T of O. Then there also exists an algorithm for the variant D, which runs in time just T of O. So actually, it's not like just like solving the decision variant can give us the solution for the optimization variant also. And similarly, solving if you can solve the optimization variant, then you can also solve if you can solve the optimization variant in polynomial time, then you can also solve the decision variant in polynomial time. So do you see why so you're right for the proof of claim one RQL, but do you see why this claim two will be true? Uh, oh, no, not little o of TO. Like what I'm saying is like you can explicitly use the black box algorithm of like the optimization variant to answer the decision variant also. And how can you do this? So essentially, what I'm trying to say is, like maybe suppose you're given the decision variant of the problem. So you're given like given a graph G. Does there exist a vertex cover with atmos k vertices? So what you do is, you just run the algorithm to solve the optimization variant, which runs in time T of O. And if you solve the optimization variant, then you know like suppose the size of the vertex cover in the optimization variant is k star. Then you just compare whether k star is less than equal to k or k star is greater than k. If k star is less than equal to k, then decision version is true, else decision version is false. RK Goel is typing something in the chat. Uh, okay, so if this is my view, did you have some other kind of doubt like? Uh, was the doubt something else? Like maybe I'm not. Maybe I missed what you meant to ask as doubt. Oh, okay, sure. I can unmute you. Just a second. Yeah, I think you can now unmute yourself.
Yeah. Hi. Yeah. So
Hi.
it was my doubt. My only apprehension here is that what if the problem. I mean, from optimization to decision
Yeah.
sounds okay. Natural.
Yeah.
I mean, this is a natural flow. However,
Hmm.
from optimization, from the decision variant to the optimization seems slightly difficult. Like the decision variant of a problem seems easier compared to its optimization variant.
Uh,
So
yeah. So you're defining this easy and hard in terms of like
easy and
like
hard in terms of, say, in terms of time.
yeah. But we just showed right that decision variant is kind like optimization variant is not much like does not take a lot more time than the optimization variant. This is like this you just mentioned yourself, right?
Yes. So what about the search variant then? Wherein indeed we need to find a solution, and not only the Boolean answer is not sufficient, and we have to actually construct the solution contrary
Okay.
to contrary to its optimization variant.
Yeah. So uh so another claim is so you are able to see my screen, right?
Yes, yes, visible.
Yeah. So now suppose we have an algorithm, actually like suppose we have an algorithm for the optimization variant which runs in time t of O, then there also exists an algorithm for the search variant which runs in time n multiplied by t of O. And do you see why this can happen? Uh,
Yes, because then while constructing the solution, I need to verify it for every input, that whether that input is a part of the solution or not.
yeah, so
So
essentially on a high level what we are going to do is like what you just said so if we have to find the vertex cover with minimum number of vertices, let's just say what I do is I select one vertex from the graph uh, and remove it from the graph and then see whether the vertex cover size decreases or not. Uh,
yes, yes,
y- like uh, do you see what I'm trying to say?
yes, I
Uh,
understood this.
Yeah, because what we want to find is like the minimum number of vertices, and then if I find one of the vertices which is part of the optimal set, and if I remove it, then the minimum vertex cover size should decrease by one, and so that vertex is indeed part of the minimum vertex cover, and then you recurse on the graphs and you need to do it maximum n times because there are n vertices.
Yes, yes.
This is I can try to explain this better if you have some doubts in it, but. Should I try to explain this better, or is it fine?
To me, this is fine. Yeah, I understood.
Oh, oh,
Because we
okay,
would
okay.
be defining every input exactly once, that whether that input is a part of the search solution or not, and that would be requiring this n factor here.
Yeah, 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 exactly. And also maybe one another thing which I should mention is yeah, like this is something which maybe is not like you mentioned what if the class D is in NP, like the problem D is in NP, right? Suppose the decision version is in NP, like decision version is NP complete, let's say. Like then what happens to the optimization version? So what I'm saying is actually so see the class NP, the specific class NP is the NP is defined for decision problems. The class NP is defined for decision problems. But the class NP hard is for any set of problems. Like the class NP hard just says that whether a problem is whether solving this problem would give you solutions to all the problems in NP as well. So, so this decision version is actually NP complete for vertex cover. because this problem is lies in the class NP as well as it is NP hard. But the optimization variant, this does not lie in the class NP because uh, like this is not a decision problem, right? So actually this is just NP hard. This is not NP complete. The optimization version is just NP hard. Do you see what I'm trying to say here?
Yes, yes, because the problem, since the problem is an NP hard, so the problem itself need not to be the element of NP.
Yeah,
But
exactly.
then this is equally hard as any other NP problem is. So yeah, in that sense, this is NP hard.
Yeah, so this is NP hard, but this does not lie in the class NP because NP the class NP only contains decision problem. So yeah, so this is an NP hard problem, but not an NP complete problem. Similarly for search version as well. So yeah, and like it's just our choice that like we try as we saw that like in terms of running in polynomial time or not, like all these problems are kind of equivalent. So decision problems are the like simplest problems to study, and that's why we kind of focus on these problems. If this makes sense. Yeah. Is it fine?
Yes, yes.
Okay. So is there anything else? But yeah, like yeah, this just remind me like this can make for a really nice MCQ question. Like suppose someone gives you the problem that given a graph G, find the size of the vertex of a minimum number of vertices, and what's the complexity class of this problem? And one of the options is NP complete, one of the options is NP hard. Then actually NP hard would be the answer. NP complete would be incorrect. So yeah,
Yes.
yeah, this might be a nice question. Yeah, thanks for pointing this out. So so uh, can should we move on to like the summary of this week's lectures, or do we have should we discuss anything other than this also before?
Yeah. So you can continue to this summary.
Okay, okay, cool.
Thanks.
No worries. So so yeah, so this week again we continued discussing about like NP hardness reductions. So for example, like one of the problems which we discussed was coloring of a graph. Uh, so a coloring, what's a coloring of a graph? A coloring of a graph G with K colors. Maybe I should enlarge the picture. Yeah. Oh, yeah. A coloring of a graph G with K colors is a function from the vertices of the graph to like K numbers 1 to K integers 1 to K. And like a coloring of a graph G is called proper if for every edge UV belong to that graph, we have that color of U should not be equal to color of V. So essentially, suppose you are given K colors, and then what you have to do is you have to assign a color to each vertex of the graph. And then what you have to, and then the coloring, this is a coloring, like basically essentially assigning one unique color to each vertex of the graph, or like one color to each vertex of the graph. And then what we have to ensure is a coloring is proper if for any edge, the endpoints of the edge should have different color. So like for example, in this graph, you can see that if you consider any edge like this edge C and F, C has yellow color, F has red color, E, such as C and E has red color and C has yellow color. So this is like, this has different endpoints, like, and you can verify this for all the edges that this indeed is a like proper coloring. Right. And since the number of colors which we use for this graph is three colors, the red color, the yellow color, and the green color, hence the graph is three colorable. And so like we call that the chromatic number of the graph is at most three. You can also show a lower bound that this graph cannot be colored by two colors. But yeah, we'll come to that later. Okay. And now the problem is, so suppose you're given as input a graph G. So what's the tree coloring problem defined formally? So suppose input is a graph G, and now the problem is like what we need to output is, does there exist a proper coloring of G with at most three colors? This is called the three coloring problem. And actually, it was shown in the lectures that the three coloring problem is NP complete. And maybe we won't go into the details of the proof of how it was derived, but just as a like high level thing of the different gadgets which we use in the proof. Uh, so essentially, how did we show that? How it was shown in the lectures? Like I did not show it. Like the professor showed. Professor Palash showed like how like three coloring problem is NP complete. So yeah. So first of all, like it's easy to see it's easy to verify whether like it's easy to prove that this three coloring problem is in the class NP. Uh, so after that, to show the NP hardness, actually the three coloring like uh, three sat can be reduced to actually three coloring problem. Uh, so and what were the gadgets used to like? So essentially, if you can solve like three coloring problem, then you can also solve three sat problem in polynomial time. And what was the high level idea? So essentially, like there were some gadgets, which tools which we like to call gadgets, which were involved in this reduction. So a triangle to encode true and false. So there was triangle which has nodes like T, F, and X, and it was a triangle. So essentially, like in the graph G, in the constructed graph G, this will be a triangle, and so all the three nodes will have different colors in this triangle because if we are looking at three coloring, then actually it should have all these nodes should have different colors. And then for each variable, we had this gadget of like x, a, and a bar. And again, like for this triangle also, we should have like different colors assigned if the graph is three colorable. And then for each clause, let's say the clause CJ is L1 union L2 union L3, where these L's are literal, so they can be of the form A or can be of the form A bar also. And then there was this gadget constructed, which was like we have these L1, L2, L3s, and then uh, L1, L2 go through this kind of a triangle, and then this further goes to this kind of a triangle, and its endpoint is T. And yeah. Proper three color and one can show that there is a proper three coloring of this gadget actually if and only if at least one of L1, L2 or L3 receive the same color as T. So what this essentially means is that like what this translates in three sat terms is like at least one of these three literals should be true, and only then uh, like like if there is a proper three coloring, if and only if like one of these three literals is true in the three sat assignment. And so using these kinds of using these gadgets and like putting things all together, we were able to show that the graph constructed will be three colorable if and only if the corresponding three sat instance is like satisfiable. So yeah, and that's how I can show that yeah the three coloring problem is in Bihar. And yeah, so just as a reminder of all the things which was shown in the lectures, yeah, so it was shown in the lectures that uh, like CNF SAT can be reduced to three SAT problems, which can be further reduced to independent set, and independent set can be reduced to clique. And similarly, also like a three SAT can be reduced to three coloring, and independent set can be reduced to vertex over. So yeah, and the second problem which was discussed in this week's lectures was the subset sum problem. And what's the subset sum problem? So suppose given a set A of like n integers and given another target integer capital T, uh, one has to output that does there exist a subset capital B of the original set A such that uh, like the sum of the numbers in the set P should be equal to T. So essentially on a very high level, what's the subset sum problem? So from this given set A, can we select subset B out of this set A? Uh, so can we select some elements of this set capital A such that some of those elements equals to capital T? So this is what is the subset sum problem. And actually, one can show that the subset sum problem is uh, NP complete. So yeah, uh, the subset sum problem is NP complete. This was shown in the lectures, and yeah, to show that the problem is in NP is easy to show, and to prove the NP hardness in the lecture, it was shown using reduction to vertex covers, reducing vertex cover to subset sum problem. So yeah, and then there was another problem which was discussed, which was the knapsack problem. So in the knapsack problem, input is a set W of n word like n elements, and like so W kind of can, you can think of this W as weight. So like there are like essentially there are n items, and each item has a weight Wi. Each item I has a weight Wi, and there's a profit associated to that item. Like profit is Pi associated to that item. So there are n items. Each item has a like weight Wi. Like each item I has a weight Wi and a profit Pi. And we are also given integers b and t. And essentially, the problem is, does there exist a, uh subset? Does there exist a subset of elements such that their weight is bounded by b, but the profit is a profit of those items is at least small t. So essentially, like what we want is we want to select some items out of these n items, so that the total weight of these items does not exceed b, but the total profit of these items should be at least t. And this is the knapsack problem. And actually, again, it can be shown that this knapsack problem is NP complete. And to show the NP, again, like it can be easily shown that this belongs to class NP. And then to show that this problem is NP hard, it was shown that the subset sum problem reduces through the knapsack. So, yeah. So we won't be getting the reductions, although the reductions are not that hard really. But yeah, uh, since this was anyways covered in the lectures, and these sessions are more like some for summarizing the week sessions, let's not get into the reduction. But yeah,
I have a
uh,
query here.
yeah.
So what that initial thought process is, and which led to this conclusion that vertex cover is the right problem, which can be reduced into the subset. So
Oh, yeah. One has to ask first of all, like, yeah, of course, like uh, when this idea first came out, I think that at that time it was definitely revolutionary. That's why like the original CARPS paper, which finds these 21 NP complete problems, was a revolutionary paper in the area of computer science. So if one is starting from scratch, like if you do not know about anything, then I think it's, if you really like do not know about like the different kinds of reductions which can be done for problems, then I really think that this is something which is very hard to think on by yourself. But one thing is like suppose now like let's say you know some time kinds of reduction. Like there are some reductions which you now know that we know that subset sum can be like I'm saying that the first like Richard Karp showed all of these reductions, and at that time certainly all of these reductions were like very revolutionary ideas. And now what I'm saying is, let's say now we know that there are these kinds of reductions available, and you know the kind of ideas involved in these. And what I'm saying is, now using these ideas, maybe it's easier to think, okay, which problem can be reduced. Like certainly, it's like not trivial in any case. Like suppose I give you a new problem, and you have to answer whether it is in NP or P, whether it is NP complete or in P. Uh, then like certainly it's not easy to classify. There are various problems which are like in research which are open problems. Like no one knows whether the problem lies in P or is in NP complete. So yeah, like what I'm saying is there is no really natural process associated to this, but at least for like At least if you know like these kinds, like if you know the proofs for these kinds of reductions, suppose I give you some very similar problem to subset sum or something, then maybe you can try to reduce vertex cover to that problem also. Like that's all I think, I guess I can say for this. Uh,
Okay, yeah, yeah, thanks. And so, is there any problem in NP and which is not NP complete?
so you're saying, is there any problem in NP, which is
Like say, yeah, which is not NP complete. Like all the problems which I have seen so far. So most
uh,
of the problems which I see here are in NP and are there NP complete as well. So
okay,
are there problems which are there in NP but not NP complete?
okay. So that's, I think that is an open question. Like no one knows. Uh, yeah. So uh, I think like okay. So uh, what I mean to say is so suppose like consider the problems lying in the hello. Am I audible?
Yes, yes, you're audible. Yeah, I can hear you.
Yeah. Okay. So so yeah. So is it an open problem? Like maybe I'm not really sure. But okay, just think of the problems which lie in the class P. Okay. So consider any problem which lies in the class P. Then
Okay.
uh, uh, that problem is kind of like if like okay, so it's not really known whether NP equals to P, right? Right. It's completely it's $1 million open problem whether P equals to NP or not. But suppose if P is not equal to NP, suppose so you know about this problem, right? Whether P equals to NP or not.
Yes, yes.
Yeah. So if P is not equal to NP, then you can actually say that any problem which is solvable in polynomial time, like, is not an NP complete problem.
I could not understand this.
Okay, so maybe I should try to, yeah, write it at the top. Yeah. So, so question. Are there problems in? Uh, okay, so maybe to simply write it as, is NP, is the class NP equal to the class NP complete? This is the uh, this is the question, right? Or maybe doubt. And what I'm saying here is like this is kind of an open, this is kind of an open problem. Uh, but it is widely believed that this should not be true. Like there should exist problems which lie in the class NP but are not NP complete. But I think it's an open problem. So why am I saying this? Uh, so uh, so what's the like what's one of the most so what I'm saying is maybe I'll just say this. If P is equal to NP, like if let's say one knows that P equals to NP, like if someone shows that P is equal to NP, then what this means is uh, every problem is solvable in polynomial time. Like all the problems in NP are solvable in polynomial time. And so all the problems in NP complete are also solvable in polynomial time. So this NP class collapses to the class P, and similarly NP complete also collapses uh, to P. So then I would assume that NP is equal to NP complete. If I'm not wrong, uh, but if P is not equals to NP, like let's say, like, yeah, P is a strict subset of NP. Yeah. Then what one can say is then like there exists uh, problems in P uh, which are uh, not NP complete, right? Because there is a problem in P which is not NP complete. Because uh, and let's call this problem let's say small p. So there must exist this problem small p in the class complexity class P, and this problem should not be NP complete, because if the small p was like NP complete, then P would have been equal to NP. Does this make sense?
Yeah, so I could not understand the first one, that if P is equal to NP, then
Yeah. Okay. Maybe I think. Yeah. The second point is clear, right? Although.
so second will make sense if the first one is okay then.
Okay. So what I mean is, okay, maybe or something. So okay. So if P is equal to NP, then uh, uh, what I'm saying is like, yeah. So what this essentially means is that any algorithm, any problem lying in the class NP can be solved in polynomial time, right? Just this statement, like if you just consider P equals to NP, what this means is that any problem in the class NP can be solved in polynomial time, right?
Yes, that will make sense because P by default, I mean, I
Yeah, by
from
default means the set of problems solvable in polynomial time.
yes, I mean from this equation, I can predict that P is equal to P complete. I do not know which first problem was proved as P complete, but P is equal to P complete seems true. Because the hardest problem in the P
Yeah,
class,
yeah,
that is P
yeah,
complete, same as P.
exactly.
So if that is the case, and if P is equal to NP, then clearly this NP complete would be same as P complete, and
Yeah,
then this makes sense that if NP
yeah,
is equal
exactly,
to, yeah, yeah,
exactly.
yes, fine, yeah.
Yeah, exactly, exactly. Like, uh, yeah, I like you can think of a class P complete, or like, yeah, you can just think of this class as P because, like, yeah, because essentially, what's the definition of this, like say NP complete class? That you are suppose you can solve a problem, like you can solve a problem of that class. Then you can have in some extra polynomial time or some polynomial calls to this problem. You can solve any problem in NP. This is what's the meaning of a problem which is NP complete, right? Like
Yes,
if a problem is NP complete, like suppose the decision problem and it's in NP, then it is NP complete if and only if like if you can take the algorithms for solving that problem and you can like if essentially you can take the algorithm for solving this problem, and with some further polynomial time you can solve any problem in the class NP. Or on a very high level, if you can solve this, if a problem is in the class NP complete, if the problem is NP complete, then if you can solve that problem in polynomial time, then any problem in NP can be solved in polynomial time, right?
yes,
If there exists a problem in this class which can be solved in polynomial time, then any problem of this class can be solved in polynomial time, right? Uh, But now what I'm saying is kind of yeah, exactly what you said. Like if if P equals to NP, then actually any problem in this class can anyways be solved in polynomial time. And so any problem in this also is can be solved in a polynomial time. And that's why like both of these classes are just equal to P only.
yes.
And that's why NP is equal to NP complete. if P equals NP.
So what about those NP intermediate problems then? Where do they stand in this gamut?
What do you mean by NP? Intermediate problems?
There are some
So you
problems which
mean the complexity classes like quasi NP?
not quasi NP. I think that I heard this term or I read this term NP intermediate in one of the
Okay.
lecture. Yeah,
Uh,
but I don't
okay,
remember
maybe I'm not
exactly.
aware of these. Maybe I'll just Google this. Because yeah, sorry, because I'm not really
No,
aware.
no issue. It was something related to isomorphism, I guess. NP intermediate.
Graph isomorphism.
Yes. Maybe that
Yeah,
is NP intermediate.
yeah. So that's also like quasi NP, like yeah.
What does it mean then?
So essentially, like uh, yeah. So essentially, like uh, uh, what we know about the, like suppose for some problem like so all of these NP intermediate classes and everything, like also we really don't know like where they lie, like uh so essentially what does that what it looks like. So there are these classes like NP intermediate classes, like so what we know about these kinds of classes is that P is a subs like every problem in P is also lies in these NP intermediate classes. And we also know that these NP intermediate classes is a subset of NP, the class NP. So like uh, there are problems uh, uh, which we know lie in the class NP, but we also know that like all the problems in P lie in these NP intermediate classes. And but then also like it's really not known whether this subset like it can be true that all of these things are equality, like these are like very big open questions in complexity theory. uh, so like what you're saying, this has an NP intermediate class. So what people like normally what people believe is that okay, it might be the case that P is not equal to NP, and then maybe there and if P is not equal to NP, then maybe there can be a superset of P which is also not equal to NP. And that superset can be thought of as like NP intermediate. But we really don't know like if there exist such problems, of course, because that would resolve the P equals to NP question. Whether there exist such problems which are not in P but are in NP.
Okay, okay. Thanks.
Does this make sense?
Yes. I understood that the superset of, I mean, some problems and which seems to be tougher than normal P
Yeah.
would be there in NP intermediate, but we are not
Not
sure.
tougher, not tougher, but saying that uh, like not because it is not strictly tougher because there is this subset equal to relation. You should rather say that not easier is the correct term to use, which seem to be
Yes,
not easier than the
not
problems.
easier. Right. Yes,
Yeah.
makes
So
sense.
there are problems which seem to be not easier than problems in P, but also so like there is this complexity class called like quasi NP. Like it's also like really interesting or like very big. Like again, these are like very big open problems in theoretical computer science. Like of course, this is the biggest open problem, and then there are some like other very big open problems, but smaller than this problem. Like quasi NP are kind of like uh, so okay, how do I define this? Mm, yeah. So suppose like on a very high level, like I don't really know the exact like technical definitions, but yeah. So so there are like problems in NP which like suppose let's say the click problem. Like if there is if there exists a class click of size, let's say n over 2, then that takes like then it's uh uh okay. So quasi NP are kind of problems for which this kind of a runtime is known, like n to the log of n. Maybe like let's forget about what I said about clicks. So if for some problem this kind of a runtime is known, uh, that like suppose n is the input size, and the runtime is like n to the log of n or something, or log square of n, then this complexity class is called quasi NP. Because why is this quasi NP? Uh, because usually with NP in the class NP, you if you try to find like if you try to solve the problems in NP, usually the runtimes will be something like this, n to the n or something. For the NP, maybe NP complete problems or NP hard problems. And then there are some problems like graph isomorphism for which this kind of runtime exists. And what's polynomial? So why is this called quasi NP? Because this is not because these kinds of problems don't behave exactly similar to the most of the problems which we see in NP hard problems. Because most of the NP complete, or maybe NP complete, because most of the NP complete problems have a runtime of something like n to the n. But we see that there are some problems actually which have runtime of something like n to the log n. So they behave kind of somewhat differently than these kinds of hardest problems, which have runtime of n to the n. So we like to call these as quasi NP. But still note that this runtime is not a polynomial runtime. So what does a polynomial runtime look like? A polynomial runtime is just something like this, right? Okay, maybe I should. Polynomial runtime is something like n to the c, where c should be a constant.
So for NP complete, would it be of the order of n raised to the power n, or just 2 raised to the power n is sufficient?
Uh,
Because
so
a deterministic Turing machine would be taking exponential time.
yeah, okay. So, but okay, am I writing this wrong? Yeah, I think what you just said makes maybe a bit of sense. But 2 raised to the n will be something like
N raised to the power n becomes huge. I think that this would be for
oh
EX.
okay not really n raised to the power n and 2 raised to the power n are really not that different because uh, uh, y- uh, you can allow some kind of a slack in this exponent, right? So like n raised you can think of this as 2 raised to the power n, or you can also think of this like you can write this n as like 2 raised to the power log n, right? And then this is also equivalent to saying 2 raised to the power n log n,
Yeah, right.
right? And I'm really not worrying about these kinds of factors. Like this is a very I'm just talking about on a very high level. Uh, I'm not really talking very formally here. So like n raised to power n or n raised to power n log n is or like something in raised to the power n or something raised to power n log n is not really that much of a difference to me.
Yes, yes.
So that's why uh, uh, this is kind of similar. But you can see that this kind of a runtime behaves very differently from this, right? There's a huge amount of gap between n to the n and n to the log n.
Yes, 2 raised to the power n log of log n here. Yeah, big difference.
Yeah.
In
So
case
this
of
will
quad.
be like 2 raised to the power log square n. This will be 2
Log.
raised to the power log square n.
Yes, yes.
Yeah. And so there are problems like in usually for NP complete problems we have these kinds of runtimes if you want to solve the problems, like the best known runtimes. But there are some problems for which we have for graph isomorphism we have these kinds of runtimes. But we don't have any polynomial runtimes for these kinds of problems. So then maybe it's possible that so then this is called like the class quasi NP for which these kinds of runtime exist. But then we really don't know whether this quasi NP, if this hierarchical, it is certainly possible that this hierarchy collapses. That it might be possible that P equals to quasi NP is equal to NP complete. But we really don't know of any separating examples for any of these hierarchies. We just know that NP complete is a superset or equal to quasi NP, which is again equal to or is a superset of the class P. But yeah, but yeah, there are even further refinements for these kinds of classes. But yeah, like I'm not really familiar with like the formal definitions for these classes, but I know on a high level what all of these mean. But this is like I feel like these kinds of things are pretty cool. Like you have problems which have like these kinds of very huge runtime. Then you have problems which are not polynomial but still huge, but not that huge runtime. And then you have like efficient runtime, and you don't really know like uh, of any problem which separate these kinds of problems. So yeah. So is it uh, are these like kinds of definitions clear?
Yes, yes, yeah. Thanks.
Yeah. So essentially, like the question which was at hand was like, is NP equals to NP complete? So what we are what I was saying was, if P equals to NP, then NP equals to NP complete. And if P is not equal to NP, like P is a strict subset of NP, then there is a problem P small p in the class capital P, like which should not be NP complete, because if the problem was NP complete, then P should have been equal to NP. And then like if this is true, yeah. Uh, this problem lies in the class P. So what this means is that this problem also lies in the class NP, right?
Yes.
So yeah. So since P, okay, yeah. Uh, since P lies in the class, yeah. So there is a problem in P, P, and since P is like P, hence it lies in the class NP, but not in NP complete, right? So then you see that like if small p is a problem which lies in the class NP but not in the class NP complete, then it means that uh, NP is like NP complete is a strict subset of NP, right? So if P is equal to NP, then NP is equal to NP complete. But if P is not equal to NP, then NP complete is not equal to NP, right?
Yes.
So what this essentially means is that, so it's an if and only if condition. P equal to NP if and only if NP equal to NP complete. So like this problem is like kind of as hard as solving the P equal to NP problem. Because if you solve this problem, then you have also solved like P equal to NP problem,
Correct. Yeah.
right? Uh, Hopefully I'm correct. Like, yeah, it, because I'm just thinking along the way, but it might be that I'm making a big blunder. But yeah, if there are any like if like I look at it later on also, and if I realize that I might have said some very idiotic things, then like I'll just correct it in the document and also like update about it in the next session.
Sure, sure. Yeah.
So, but yeah, from what I understand right now, yeah, the class NP, like it's an open problem, whether NP is equal to NP complete. Yeah. Okay then. Okay, maybe I can just like just do a quick check on Google also, like just for sanity check, so that uh, Yeah, I think I was correct. Yeah, I just checked on internet also, and yeah, I think this is true. So yeah, it's it's good that yeah, I did not commit any error. So, yeah. So this is an open problem. So can we move ahead uh, with the summary, or do you have any doubts with this, RK?
Yeah, so you may continue with the summary. In the summary, I have one more doubt related to that sign you have used for the reduction. So what kind
Uh,
of the reduction
mhm.
are we doing here? Is this the car reduction or the many to one reduction? Uh,
Where so sorry, where
like
was
say,
the
yeah, so somewhere you use this P along with this reduction symbol, and probably this P stands for the entire reduction has been carried out in the polynomial time. And yeah,
yeah,
like this vertex
yeah,
cover
yeah,
has been used.
yeah.
Okay, yeah. And somewhere you missed this symbol. So because sometimes we use this M here and sometimes we used P. Probably M stands for the many to one reduction and P for this car reduction, I guess. So
Okay.
so what's the difference? And so when do we use which kind of the reduction? Because I heard three reductions, many to one, and then I do not know whether they all are distinct or same. Many to one, and then carp, and then Turing reduction. So when do we use
Okay.
which reduction? Yeah.
So I don't know about many to one reduction so carp and Turing reductions are again like two sides of kind of the same coin. Suppose I give you so carp reduction essentially says that you try to show equivalence of a problem with another problem. Like if a problem's yes instance, a problem is a yes instance if and only if a given instance is a yes instance if and only for some other problem. The some other instance the yes instance. Whereas in Turing reduction, you kind of say, okay, I'm given a black box which solves some problem A. Then using this black box, a polynomial number of times and some additional polynomial time, can I solve the problem B? Right? So, uh, like, uh, uh, it's not really personally, what I feel is like it's not really necessary to uh, think about like these car reductions or Turing reductions or everything separately, because in the end, at the end of the road, like all these reductions are trying to classify problems as lying in classifying problems as NP hard or not. So you can show NP hard if you can show NP hardness by car reduction or Turing reduction, like both of these things are fine. Like because in the end, we are like what we really want is showing the NP hardness. So, but yeah, just as a question, just to answer your question, like what kind of reductions did we use to answer this? So in this recoloring, actually the gadgets and everything which we constructed, so it actually was a type reduction, because what we said here was we constructed some graph G and we said that this graph G is three colorable if and only if the given three sat instance is uh, satisfiable. So this is why it's a class reduction, because the from a given instance of a known NP hard problem, what we have done is we have constructed an instance of uh, the other problem which we want to, of the three coloring problem which we want to show that like these instances are kind of equivalent. So this was also a class reduction, and like for subset sum also, what we actually showed was uh, we mapped an instance of a vertex cover to an instance of a subset sum. So again, that was also a class reduction. And I think for set cover also it was a class reduction, because we mapped an instance of a set cover to an instance of a vertex cover. So I think most of the reductions were car reductions actually. And an example of a Turing reduction would be this reduction. So this is a Turing reduction. Suppose we want to yeah reduce the decision variant to the optimization variant, or we want to reduce the optimization variant to the decision variant. So what we say is like we take the algorithm for solving the decision variant and run it log n times, and that's how we solve the optimization variant. That is a Turing reduction because we have taken a black box and we have run it polynomial number of times to solve some other problem. So this optimization variant was some other problem which we solved using like log n number of calls to the black box oracle of the decision problem. So this is a Turing reduction.
Yeah, yeah. Thank you so much. Can you please indicate this thing here in the claim one that this is the Turing reduction, so that later on
Yes,
when I see these notes, yeah,
of
this is
course.
like, yeah, thanks.
This is a but like personally like what I feel is like okay these terminologies exist but yeah at the end of the road, the uh, all of these reductions are meant to do is like these are just landscapes to find uh, like whether the complexity class of the underlying problem. So when you're thinking about reductions, I would advise you to not like if you're thinking about reducing some problem to some known problem, I would advise you not to think like okay, do I do carp reduction or do I do Turing reduction? Like anything works, like as long as it's a valid reduction. But yeah, this is a Turing reduction since we are calling the we call the black box algorithm for D uh, log n for D to solve the yeah log n number of times to solve the problem of
Yes.
yeah and it fine. Hmm? Hello.
Yeah. So how complex this function f would be? Like say if I'm reducing the this one problem, like say the vertex cover into the other problem. What was that? The subset sum problem. So whichever function I'm using to carry out this reduction, can this function be more complex than the classes of the problems themselves? Like say if this subset sum is element of NP, then can this
Yeah.
reduction be more complex, or has to be, it is mandatory that it has to be less complex than the complexity of the problem itself,
Oh yeah.
because you don't
So
be there.
yeah. So yeah. So actually. Yeah, so that's a really good point. So in car reductions, like this is also mandatory that like you can have these kinds of like functions, but this function should be computable like in polynomial time. Like so you should be able to make an equal like for this recoloring you should be able to make the like like to reduce like 3 sat to 3 coloring. You should be able to reduce 3 sat instance to a valid 3 coloring instance in polynomial time. So it should be we should be able to do that part also in polynomial time. Yeah, that's a really good point.
And what if I am reducing a problem which is in P class into another problem into the P class, then can I still use a reduction function which runs in the polynomial time, wherein
Yeah,
both the
of course,
classes and
because
both the ends are polynomial?
yeah, because in the end we just want polynomial, right? So as long as it does not break the polynomial assumption, we are completely fine.
All right, yeah,
Yeah.
thanks.
Yeah, it can be that like if you are reducing one problem in P class to another problem in P class, it might be that the reduction might take like P like if the original problem runs in let's say order n time, it might be the reduction takes order n to the 100 time. But it's completely fine because in the end we are still in the P class.
All right, yeah.
Yeah, so that's a really good point. All these reductions which we are carrying out, yeah. have to be like these reductions have to be carried out in polynomial time as well. Yeah, thanks for pointing this. So like I kind of forgot. So yeah, oh, I think uh, yeah, we were discussing. Yeah, I think we discussed that. Yeah, set cover. What's the set cover problem?
We discussed knapsack here.
Oh, okay. Yeah, sorry. So, and then there was this, and then there's another problem which was discussed in the lectures, which was the set cover problem, where suppose we are given as input a universe U and a collection of subsets like S1 till Sm of U, and we are given an integer k, and then we have to find that there is report does there exist a subcollection W of S such that uh, union of like all the subsets of this subcollection W should be the whole universe and the size of this W should be less than equal to K. So essentially you can take like, so essentially you have to find like at most K subsets out of these given M subsets such that their union gives you the universe U. And then this problem, this set cover problem is also NP complete. And uh, uh, this was like to show the NP hardness again for the set cover problem. It was shown that vertex cover can be reduced to the set cover problem. So if you have a like solution for set cover problem, like so any instance of vertex cover problem can be converted to an equivalent instance of a set cover problem. So yeah, and mapping the whole landscape, which was discussed in the lectures. So there were these kinds of reduction solutions in the lectures. So first it was shown that CNF sat the original like the problem which we started with like the problem which is like the NP hard problem like which was shown by Cook like this was the foundational problem showed by Cook-Levin theorem that CNF sat is NP hard, and then using the CNF sat we proved that we saw that like CNF sat can be reduced to 3 sat, and then this 3 sat can further be reduced to independent set, 3 coloring, and subset sum. And this independent set can be reduced to vertex cover and clique, and this vertex cover can be reduced to set cover. Similarly, this subset sum can be reduced to knapsack. So this was the landscape of, I think, the problems which were discussed in the lectures. And of course, like although like you are reducing like let's say CNF SAT to 3 SAT, then to independent set, then to vertex cover, and then to set cover. So, but this does not mean that set cover is a harder problem than CNF SAT, because we also so set cover lies in the class NP, and we know that CNF SAT is also NP hard. So actually, by the Cook-Levin theorem, actually, uh, yeah, these two problems like set cover can also like we know that CNF set can be reduced to set cover, but by the Cook-Levin theorem, like there's a bidirectional arrow, so set cover can also be reduced to CNF set. So like why I am saying this is because I think like everyone needs to realize the like importance or like the significance of Cook-Levin theorem. Like it's like the I think one of the biggest results in theoretical computer science to ever come out. Are you saying something, RK?
Yes, yeah. So the issue, I mean, in this hierarchy is like reducing, I mean, an instance of a Boolean expression as an instance of graph, say. So
Mm-hmm.
that becomes very difficult and difficult to understand as well. Like you also talked about those gadgets, etc. So by
Mm-hmm.
using those things, we are converting an instance of the Boolean algebra into an instance of graph. So is there any easier way to carry out this conversion wherein the Boolean expression need not to be directly converted into a graph instance, and there is something in middle or something which is easier to
Um,
understand? I hope I could clarify my question because yeah.
yeah, I think so. You're kind of saying like going from these Boolean expressions to these independent sets in graphs seems kind of like very out of the blue.
Yes, yes.
Yeah, like yeah, I think like if someone is doing it for the first time, I definitely think it's very new, and that's why like so all these results like initially came out like so they were like in the 70s paper or like, I don't remember the years, but like there were set of 21 problems like which map like this CNF sat to like 3 sat and all the problems in graphs. This was a paper by Richard Karp, and it is also very celebrated paper. So I would okay, I don't know why is it scrolling up and down on its own. So what I would say is yeah, if you are feeling that this is very out of the blue, then yeah, I also share the same sentiment that it is indeed out of the blue. But once you know the reduction, like once someone tells you, okay, like maybe 3 sat can be reduced to independent set like this, then I think it's easier to get an intuition out of this. So let's say maybe so like I can't answer like how to think like from scratch like about these problems, but like if you know some reductions like how some of the reductions worked out and what's the intuition behind them, then maybe you can have like an idea of like how to approach future problems as well. So for example, suppose there was this three coloring problem, and suppose like we tried out like reducing three sat to the three coloring problem. Then what was the intuition behind like defining these kinds of gadgets? Of course, like you have to find really the graphs which make all of these things work. But the intuition behind these kinds of gadgets is okay. So there are like two kinds of so there are kinds of like different variables. Like for any variable a, there are two literals a and a prime. And similarly, these a and a primes can be assigned the values true as well as false. And then what we kind of want is okay, like so suppose like if I have a very high level idea in mind, maybe like what I can try to show is that okay, like uh, uh, if a if like suppose in the three sat instance, if the a takes value true, then in this graph, this a and the node this node a and the node t should have the same color. So do you get what I'm trying to say, Arkiko? Like this is like if someone has to start out to find this reduction, maybe one step to go ahead will be okay, like if like let's say the variable a takes the value true, then maybe in the three color instance of the graph, the node A and the node T should share the same color.
Right, right. So basically, this triangle is being formulated equivalent to a literal, whose value somehow came out to be true or false, depending upon whether the adjacent vertices are having the same color or not, kind of.
Yeah. So yeah, like it's not really easy to construct such graphs, but yeah, like the intuition behind doing all of this is something like this. That maybe like I want to have that like if a variable is true, then it should share the same color. If a literal is true, then it should share the same color as the color of this vertex T. And this A and A prime should have different colors because they cannot have the same color because like I if A is true, then A prime has to be false. And that's why they have an edge between them to have different colors always. And yeah, this node X is just introduced to make things work. But yeah, like I definitely agree. Like for a first time reader, this thing is very, very non-trivial. Like I like like even even if like for me also like if I have seen this reduction, like let's say if I have not seen this kind of a reduction for an year or more, then it will be very hard for me to come up with this reduction by myself after a year also. So yeah, the thing is, I think like if we are doing these studying these reductions kind of frequently, then you kind of get an idea of okay, like how can I manipulate the graphs, or like how can I obtain the gadgets required to like solve the problem at hand. But yeah, there is no specific recipe or anything because yeah, I think there are a lot of open problems in this domain as well. Like people don't know whether some problem is indeed NP hard or not. Because it feels like problem is hard, but yeah, one is not able to come up with such reductions or something. So yeah, like
Yes,
I think
yes.
that's what I can say from my end for this. Yeah, but yeah, it is definitely true. Like that one should be amazed. If you are not amazed, then maybe you are not understanding these things properly. At least in my opinion, like one should be amazed when one sees this kind of reduction for the first time. Yeah. And then there was this notion of weakly NP complete versus strongly NP complete discussed in the lectures. Yeah. Not really complicated notion, but yeah, like our problem is strongly NP complete if it remains NP complete, even if all the input numbers are encoded in unary. And for example, the three-set problem, clique, vertex cover, independent, etc. And what's the weakly NP complete problem? A problem is weakly NP complete if it is NP complete when the numbers are encoded in binary. So a weakly NP complete problem is essentially a problem uh, which is only NP complete when the numbers are encoded in binary. It becomes polynomial time if the numbers are encoded in unary. For example, in subset sum or knapsack problem, you may have heard of like uh, uh, DP based algorithms for these problems, where the runtime is dependent on the weights, the sum of the weights of different inputs. So if weights are given in actually unary, then you actually need the like for a weight W, you actually need W weights. So you actually need a string of length W to express the weight W in unary. But if a weight of W can be expressed in just log W weights, if you are dealing in binary. And so if the runtime is like order of W, but the input size is just log W, then it's exponential. And that's why the problem is NP complete if the problem is encoded in binary.
So I could not understand this weekly NP complete thing, and especially
Okay.
this unary and the uh, binary thing.
Okay.
Uh,
So maybe, yeah. To continue.
yeah. So, but yeah, we solve this knapsack problem, 0 1 knapsack problem using DP. But then whatever solution we get, like the complexity we get of the order of NW, but then
Yeah.
that solution is pseudo polynomial, I guess. And
Yeah.
there, then there is a whole family of the problems. I don't know.
Yeah.
FP test is what is that?
Oh, no, no,
Uh,
no. FP-TAS is approximation algorithm.
approximation.
That's
Yeah,
different.
yeah. So
But
this
yeah,
unary and binary thing is not clear to me.
yeah. So yeah, yeah, definitely. It's also a bit confusing at first. So maybe like uh suppose so suppose this kind of I don't remember the exact complexity for knapsack. Uh, but suppose yeah uh like the DP algorithm, like I don't remember the exact complexity. It can also be different. But yeah, suppose the knapsack problem can be solved in like order. Like let's just suppose for now, like it might be like n cube or something like n cube times W time. Okay, here like W is the sum of the knapsack weights.
So this is NW only. I mean, not N
Okay, it's
cube.
only NW.
Yeah, yeah.
Yeah. Mm. Oh yeah, of course, it's NW because you have yeah yeah. So like I'm why I'm saying suppose because I'm not discussing the algorithm for knapsack right now. So let's just say for someone who is not familiar, so let's just say suppose this is true, right? Uh, then what I'm saying is if the input, so what does the input of a knapsack problem consist of? Input to a knapsack problem. So what does it consist of? So essentially, uh, there will be n items. So n items, and each item is kind of index by a like weight of that item I, comma, profit from that item I pair. Item I has a weight and an associated profit pair. And now suppose this weight, like so so this weight should also be given as an input, right? So this should also be part of the input, like the inputting user has to give me this weight W. And suppose like uh, okay uh, to encode WI in binary, how many bits do we need? Like, so to encode this value WI, so the user will have to give me an input string, right? And in an input string, somewhere along the line, there should be this weight WI. And this weight WI, if it is in binary, like how many bits do I need to encode this WI in binary?
Log W.
Yeah, exactly. Yeah. So log WI bits are needed, right? Uh, so essentially, like, so so if W1, so let's say it's like so the total number of bits which are needed are like log of W1 plus log of W2 plus log of W3 till log of Wn, right? And so note that but what's the runtime look like? So runtime looks like n times W, like uh, so like approximately what you can say is so uh, input ha input. So what? How long is the input? So input is like if there are n items, then like input is like kind of log W bits long, or like n log W uh, bits long, right? Because like there are n items, and like something like this is the length of the input. And now what we are saying is okay. Input is like input has a factor of log W, whereas runtime has a factor of W. So if like this log W is like something like K, then this is like a e to the K or 2 to the K or something like that. Yeah, this is 2 to the K if this log W is K. Uh, does it make sense? Okay, testing
Yes,
here.
yes. Yeah, yeah.
Yeah.
Makes
So
sense.
then it's not a polynomial runtime, right? Because if log W is K, then with respect to this input size, which has like K bits, like this, it has the runtime has a factor of 2 to the K. And hence like this is not a this is not a polynomial time algorithm uh, if the input is in binary, since the order nw runtime is exponential uh, if the input is in binary, right?
Yes.
Yeah, but if the input was in unary, like suppose you did not have bits as input, like how was this wi? So what do you mean by unary? So a weight wi uh, corresponds to w1s. Like suppose like in binary you have two alphabets, right? 0 and 1. But suppose there is another language which has just one alphabet, which is just ones. Then how do you write one? Like in unary, uh, but in unary, uh, how is one written? So one is just one. So maybe u of one, like unary of the value one will be just one. Uh, unary of two will be 1 1, because 2 times 1, because you are just like one symbol now, like you are just this alphabet 1. And now how do you distinguish between this 1 and 2? You have to write this, if you write this one 2 times, then it actually means 2. If you write this 1 time, then it actually means 1. Unary of 3 will be 1 1 1, and so on. And so unary of W will be 1 1 1 1 1 W times. So does this make sense? Like what I'm saying, like what do I mean by unary?
Yes, I understood this thing, but what is the real position of the knapsack algorithm then? Is this weakly NP complete or the stronger one?
Yeah, it is weakly NP complete.
Oh, I see. Yeah, all right.
Because in unary, like, so in unary actually now you can see that the input size is also W bits long. Like it's not log W, but input size is now W, like order of W, because this string has W length. And we have a runtime of n times W. So it's like linear in W.
So what if I make the statement that it's okay that the complexity of the 01 knapsack is of the order of
Mhm.
is
Yeah,
right
is of the order of.
is of the order of say NW, but since it may so happen that W may becomes exponential in terms of the number of the items. Like say if there are 5 items given in the problem, and it may so happen that the sum of their weights came out to be say more than 32,
Mm-hmm.
and which can easily happen. So therefore, this algorithm is pseudo polynomial in nature. Is this reasoning incorrect, or
Uh,
is this
it's there's a flaw in the reasoning actually, like because the input is not just n. Input is n along with these wi pairs also,
right? Right.
right? So you have to incorporate both of these things. Like so, suppose like for example, like yeah. So knapsack runs. So maybe let me just complete it. So knapsack runs in polynomial time uh, if the input is in unit. Yeah. So let me just complete. Let me just try to say this example. So suppose there's a function which takes as input f of x comma y, and this function is x square uh, plus y square. So will you say that this function is polynomial in the inputs f, x and y?
Yes, this is polynomial.
Yeah, but like if I think of say let's say your reasoning, like maybe let's say y is very big, like it's 2 raised to the power x.
Oh, yes. Yeah.
Yeah. So you have to essentially consider all the inputs together.
True. True.
So does this make sense then? Like why is it like if the input is in unary, then it is always polynomial time.
Yes, I understood this. Yeah. Thanks.
So yeah, but yeah, so that's why this algorithm, like this kind of a runtime, uh, is like also called like pseudo polynomial time algorithm. Like this is a pseudo polynomial time algorithm because this looks polynomial. Like this is pseudo polynomial because it is polynomial if the input is in unary. If input is in binary, it is not polynomial. So that's why it's pseudo polynomial. And then so after this, yeah, after this strongly versus weakly NP complete, like there was a bit of uh, like introduction about going beyond NP completeness. So if you know that a problem is NP complete, well, we can try to bang our heads and try to solve the problem of whether P equals to NP or not. Or and we can get stuck on this problem 50 years, or we can try to make progress in some other direction, which is like, okay, assuming like uh, this problem is hard and leaving it for the future, whether P equals to NP or not. Let's try to nonetheless design some like ways around solving these NP, like these NP complete problems. Uh, so for example, like one way is to approximate, to find out an approximation algorithm for the problem. So yeah, just thinking. Yeah. So, so suppose our objective was to maybe like, so suppose there was an optimization variant, like we were supposed to find the minimum vertex cover, like minimum vertex cover is like NP hard problem. Um, but now can I approximately answer the question? Like, so can I design a polynomial time algorithm, which is always guaranteed to maybe not give the like minimum vertex cover, but maybe give a vertex cover which is like not too far away from the optimal, like which is always, let's say, too approximate to the original, to the actual solution. So this is what is the approximation domain of approximation algorithm. And then there is this domain of parameterized algorithms, uh, where we try to run efficiently on some subset of instances where the given parameter is small. Suppose there is an algorithm which runs in time, let's say, like there are two inputs to the algorithm, which is like x and y, and let's say the algorithm runs in time x times 2 raised to the power y. But suppose someone says to you that y is always going to be small, like y is always going to be 10 or something, then that algorithm becomes polynomial time algorithm. And this is the domain of parameterized algorithms, like studying the complexity of algorithms, assuming some parameter is small. And then yeah, one way to move around is heuristics. Like NP completeness implies that there is no polynomial time algorithm for all instances, but we can have algorithms which run efficiently and probably using some heuristics solve the problem. So yeah. And then
So,
this yeah actually go ahead.
I have a query here. So, is there a tipping point or the threshold available? Say, like beyond that threshold, the problem becomes all of a sudden the problem becomes very difficult. Otherwise, the
Like
problem is manageable to be solved.
uh like what threshold do you mean? Like threshold in
So,
terms of
yeah. So, I mean, in the context of this heuristic thing, so like, does there exist a threshold for a problem instance? Say, if the size of the problem instance is lower than the threshold, then it can be solved, can be managed. However, if the size of the instance grows beyond that threshold, then the problem becomes computationally intractable kind of thing. Do we have such tipping points or the thresholds available, or
mm,
the statement is generic and general and
yeah, I think yeah, like heuristics are very specific to the problem at hand, and you can yeah, you can design like heuristic, like one can of course like what I'm saying is like there can be multiple heuristics. Like one can design a heuristic, okay, like if this parameter is, let's say the problem is still 100, the size input size 100, solve this problem using this algorithm. If it is greater than 100, maybe just give some other output or something. Like heuristics are kind of very problem and like implementation dependent. So yeah, I don't know if I can comment on them. But yeah, like definitely this is one of heuristics which I believe can be used, which some people might be using for some real world problems, like having a tipping point.
I ask this query because lot many set solvers are available online and which
Yeah, and
solve.
they usually do these kinds of things, right?
Yes, yes, yeah.
They reduce the original problem to like smaller problems, and they solve the smaller problems efficiently, and then come together to solve the final problems. Yeah,
Yes,
but yeah, like again, like that's specifically for SAT solvers. This heuristic might not work for vertex covers.
yes, right.
So yeah, like what I'm saying is like this heuristics is like if you are open to heuristics, then you are open to a lot of different ideas. Like then you're in heuristics, like you're actually not always guaranteed like worst case optimality or something, but you then say, okay, we are dealing with real world instances, and maybe for those instances, uh, the problem is done. Like the problem can be solved. Like usually, like you might have heard like linear programming. Like you do you know about linear programming?
Yes, yes, yeah.
Yeah. So in linear programming, like uh, so theoretically, linear program like uh, algorithms which could solve linear programs came up in like late 70s or 80s, and they were like in theoretical computer science, in the domain of theoretical computer science, like they were a big revolution, like revelation that okay, like linear programs can actually be solved in polynomial time. But people had been using like algorithms which like theoretically could be proven to have exponential runtime. Like the simplex algorithm can theoretically be proven to have exponential runtime. But actually in real world, like practical scenarios, even since like 50s or 60s, people were using simplex algorithm and it was running quite fast. So yeah, so sometimes like some heuristic based algorithms can outperform theoretically best algorithms on real world instances. On worst case instances, of course, like it might be that heuristics fail and uh, these kinds of ideas are needed. But yeah, a lot of times heuristics can help in like designing efficient algorithms for real world stuff. But then why do we study but then why always not just study heuristics? Why do we even study these kinds of theoretical domains? Because of course these improve our mathematical understanding of the problems at hand, and these new insights can lead to even better heuristics. And yeah, so something like that.
Yes, yes.
Okay, so Indian Ocean, so you are asking the chat like can we please change the problem solving session day and timing? So, I'm really sorry, but I don't think it will be possible because, yeah, I'm not available on other days during these timings. So, I guess we'll be sticking to this Tuesday 6 to 8 p.m. timings only. But anyways, the recordings of these sessions are always uploaded on YouTube. So even if you miss the session, you can watch the recordings uh, on the YouTube on the links which I shared with you. So yeah, uh, so on that and that's what I meant to say that yeah you can you can so by tonight probably this recording will be uploaded to YouTube, and also the document which I'm discussing will also be shared with you. So then you can just view the recording and see that and read the contents of the discussion. So yeah, thanks a lot. And then there was this, so continuing with the lecture summary, so then there was this notion of self-reduction. So self-reduction is just very what we just what we had discussed previously, reducing the optimization version to the search version. Reducing the search version to the optimization version. How can we reduce the search version to optimization version? It's kind of what self-reduction is. Like maybe solving the problem uh, in smaller instances can solve the bigger problem. So yeah. And yeah, then there was this notion like a formal definition of approximation algorithm. So we say that an algorithm is alpha approximate, like if like it like if it kind of like alpha approximates the objective in some sense. So the value given by the algorithm divided by the optimal value for the specific instance x should always be bounded by alpha. If this is true, then we say that yeah, the algorithm is alpha approximate. And for minimization problems, this alpha is always greater than equal to 1 because you cannot have anything smaller than opt. So your val of x will always be at least 1, like will always be at least opt. So this will be at least 1. And for maximization problems, usually you define, yeah. And for maximization problems, your solution will always be worse off than the optimal solution. So that's why in that case, alpha will be less than equal to 1. And then in the lectures, I think the last thing which was discussed was the randomizer approximation algorithm for max 3 sat. Yeah. Uh, Maybe you can go over this by yourself. So the algorithm and the proof like was not really too hard, but like let's say the problem at hand is like max 3 sat problem, which is like suppose as input we are given a 3 sat formula, and the output should be an assignment of a variable satisfying maximum number of clauses which are possible. And then there is the randomized algorithm, which just says that, okay, assign every Boolean variable true or false with probability half. And in this, you can actually show that this algorithm will be like 7 by 8 approximate. Like 7 by 8 of all possible clauses will always be satisfied uh, if you have this kind of a like assignment. Okay, then so we are like almost out of time. So maybe we like anyways, it's good that I just had one question prepared for today. So maybe we can just discuss this question. Uh, so yeah, so article in Indian Ocean, I would like you guys also to think about this. So suppose the question is like, what is the minimum value of m so that every two-side formula with at most m clauses is satisfiable? So two-side formula is essentially uh, it's a CNF formula where like each clause has just two literals. So the problem at hand is like, what is the minimum value of m? Uh, so that every two-side formula with at most m clauses is satisfiable.
So this two set is there in P, and with the two literals, I can have four clauses, and
The number of literals in each clause is
two.
at most two, but the total number of variables can be n or something, right? Can be arbitrary.
So two set would mean that there are maximum, I mean, exact two literals in every clause. Is this?
Yeah,
Yes. So, but then I can have any number of the variables. Is this?
yeah. And then like you have to find that the minimum value of m that every two-set formula with at most m clauses, whatever be the number of variables, is satisfied. Okay, let me just think it myself. Okay, I now feel it might be that yeah, this minimum value of m so that every two-set formula with at most m clauses is satisfied. So let's just say, for example, like suppose m is equal to 1. Like, okay, I think we'll also need to incorporate the number of variables n in here. Uh, or do we need, or we uh, don't need? Let me just think about it myself. Yeah. Oh, yeah. So suppose if I try m is equal to 1, like I'm supposed to find minimum value of m. So so if m is equal to 1, so essentially then what this claim is that every two-sat formula with at most one clauses is satisfiable. So is this true? Like every two-sat formula with at most one clause is satisfiable.
Yes, and where is the issue? Because if it is there in the CNF, I just need to ensure the satisfiability of only one literal in the variable. So
Yeah, so
I can
if it is
always
in CNF, yeah, it should be possible, right? Yeah, and yeah, as you increase the number of clauses, it becomes more difficult to satisfy. But if you're just given one clause, then it always will be easier to satisfy, right? Hello?
Yes, yes.
Yeah. Oh, yeah. So then I think, yeah, it's not that. So yeah, why I gave this question was because in this week's assignment, the same question is for three sat formula also. Like what is the minimum value of m so that every three sat with at most m clause is satisfiable. So I just thought maybe we'll change it to two sat and discuss in this session because we can't directly discuss for three sat as it's in that. But then for that also only one clause will be enough. Like or maybe it won't. I don't know. Like I feel it should be enough. It might be I'm thinking like something wrong. But it feels that yeah, I think it should be always true, right? Even if you have three sat formula, four sat formula, it does should not matter, right? If you have one clause, then that clause will always be satisfiable because then it's just some or of some literals, and then that or can always be set to true. Yeah, I think. Yeah. So I think answer for this should be just one. Yeah, because one zero is of course not the answer, and for one, you will always have this. Yeah, as yeah, one clause is just union of literal, which can always be set to true. So yeah, so that's why the answer for this is just one. Yeah, I had some plans for some other questions also which I had not written down, but I guess since we are out of time, like maybe it's better to not discuss those questions at all. So come, so I think RK, will you have some doubt that uh, if you, what about DNF satisfiability? So if the clauses are in disjunctive normal form, right? Yeah, then that question is more interesting. Yeah. So if you are talking about, let's just say, two sat in DNF form, then yeah, I think the answer in that case, mm, yeah, if you just have one and if you have, in that case, like for DNF, I think, Akikoil, you can you can have any arbitrary number of clauses, and it is like not always guaranteed to have satisfiability. Like why am I saying this is true? Because like suppose every clause has variables of this form. Like in DNF, like all of the clauses will have like ands between them. Suppose like in the first clause there is a like x1 and x1, x1 and x1 bar, and similarly in the second clause there is x2 and not x2, x3 and not x3 in the third clause, x4 and not x4 in the fourth clause. So if so all of these clauses, like whatever value you assign to x1, x2, x3, x4, and everything, uh, this clause will never be like the union of these clauses will never be satisfiable. So for DNF sat actually, I think you can like never ensure satisfiability, if this makes sense.
So Cook-Levin says that the CNF satisfiability is NP complete. So what about
Yeah.
the DNF satisfiability then? And moreover,
Oh,
in yeah,
oh, you mean complete? Oh, you should think about it. Like, yeah, I can just claim that DNF satisfiability is like polynomial mapping. It's polynomial time solvable. Like, if you are given a expression in DNF form, then uh, final satisfiability is like polynomial time. And what's the algorithm for this? You should try to figure out yourself. It's not too hard.
okay. But
Yeah.
then every DNF can be converted into the CNF. Is this true?
Yeah, but the size of the CNF will be exponential. Like if
Oh,
you, so I presume what you're trying to is you're trying to solve CNF by converting into a DNF, and then you have a polynomial time algorithm for DNF.
yes, yes,
That's a
yes.
really good way to think about it. But unfortunately, the number of like if you try to convert uh, CNF to a DNF, the number of clauses blow up by exponential amount.
Oh,
So
I see.
yeah. So this is where the concept which we were discussing previously, like the car production and everything, should have polynomial time reduction. Here the reduction itself will take exponential time.
Oh, yes, yes. All right. Yeah.
Yeah,
Thank you so
yeah.
much. Yeah.
But that's a really good way to think about it. Yeah, yeah. So okay, then I guess this was it what I had for today, and I think we are pretty much over time. So maybe if there are like we can take one more question, like let's say from Indian. So Indian Ocean, if you have any doubts, maybe we can take that before closing the session. Okay, so I guess since Indian Ocean is okay, Indian Ocean is typing. Okay, how to know which problem we can reduce our new problem, which is NP complete. Yeah, Indian Ocean, there is not really, like I think Archegol was also asking this, but there is not really a set, like I said, a set structure to this. The only thing which can I can advise you is like go through the reductions which you know, like the reductions which have been covered in the lectures, like just go through those reductions first and get a feel of how they are done, so that you have a so that one can have a high level idea of like what kind of problems can be reduced to what kind of problems. But this is like there is really no specific idea or like a specific way to go about it. It's just doing it on the fly. Like though going over the reductions which are like already known, like the ones which are discussed in lectures, you should definitely go over them and understand them properly, because this definitely helps in developing an intuition of how to go about newer problems. So yeah, that's all I can say from my side, that yeah, go over the reduction discussed in the lectures like very carefully, and then hopefully you will be able to reduce new problems also. But yeah, this is really this is what not really easy always. Mm. Okay, so uh, both of you guys are typing something.
In fact, I was not writing anything. I was just saying that this session was very useful. Yeah. Thanks, Ita.
Oh, okay, okay, yeah. Thanks a lot. So hopefully, I like in the previous few sessions, I don't think anyone joined in person, but hopefully, I'll see you guys in person from next week again. Yeah, for like I guess previous couple of sessions, like I was just teaching by myself in the on the YouTube recordings. But yeah. But yeah, thanks a lot for joining today, guys. And yeah, thanks a lot to everyone who is watching on YouTube also. So hopefully I'll see more of the guys who are watching on YouTube in person. Okay, my mail ID Indian Ocean, I can type it in the chat so you can uh, contact me at this mail ID. But yeah. So okay, then I guess there are no more doubts, and like yeah, we don't have a lot of like we have way over time now, so I guess we can now close the session. So yeah, thanks a lot for joining, guys, and yeah, thanks to everyone who's watching on YouTube. See you guys next week, same timing, Tuesday 6 to 8 p.m. So I'll be closing the session now, guys. Thanks a lot.
Thank you so much.
Bye
Bye.
bye.